went to a show. They dropped me off at Grandpa Joe's. I kicked and screamed, said please don't go. Grandma take me home, 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 Grandma take me home. I had to hit my dinner there, mashed potatoes and stuff like that. I couldn't chew my meat too good. Grandma take me home, 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 Grandma take me home. Said why don't you stop crying? Go outside and ride your bike. That's what I did, I killed my dog. Grandma take me home, 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 Grandma take me home. After dinner I had ice cream. I fell asleep and watched TV. I woke up in my mother's arms. Grandma take me home, 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 while I feel alone.
Okay, so everybody had a successful lab 1 yesterday. There were a few snags, but hopefully we'll work through them. But for the most part, everybody was able to go through the process of creating a program, compiling it, running it, and handing it in and being graded on it. Before we get started today, I want to draw your attention to an event almost immediately after this. It's the Involvement Fair. So RSOs, which are recognized student organizations, clubs, sports clubs and academic clubs and activity clubs, they're all going to be having over 150 of them are going to be at the Nebraska Union from 4 to 6 tonight or this afternoon. And in particular, I'm going to plug a couple of them, like the CSAB will probably be there, ESAB will be there. That's Engineering Student Advisory Board and the Computing Student Advisory Board. Basically, student governance for computing and engineering, respectively. Also, there's going to be Corn Hacks is going to be there, which is our annual hackathon, which is usually done sometime in the very early spring semester. And even though you're only going to go through CS1 by that point, you should still consider, signing up and seeing what it's like. At least there's free food, free and prizes, of course. So go ahead and check it out. There are 150 other organizations there as well. I'm sure that the UNL Gaming Club will be there too. I'm also the advisor for that. So if you want to, go ahead and meet them, join their Discord, and then they have game jams each semester. Everybody builds a game and then shows it off at the end of the semester. All right, so to pick up where we left off last time, this is a more complex program here. Before we get into it, I want to just look at this program and think about what it does, right? So the program itself, the source file for this is named KMS to mile, right? Or KMS to miles, I forget miles, plural there, right? Can you immediately tell, without even looking at the code, what it does? What? It converts miles to kilometers. This is called documentation, right? This is it's in a comment, and we'll talk about comments in detail. But otherwise, it's a header documentation. We've got an author, a date, and if I was working with somebody, then I would put their name here as well. And then the purpose of the program here, right? We've got so obviously it's going to convert miles and convert miles. It's going to read miles in from the user, convert that to kilometers, and then probably output it in some way. Without even knowing any coding here, we could probably walk through this and understand what it does a little bit because it's a well-written program with good variable names and good style. We've got these are called variables, right? Just like in math, variables can vary, their values can vary and change. And so we've got a variable named miles and a variable named KMS, right? We've got this print statement that says, please enter miles, right? And then a scan statement. So obviously what's going to happen is the program is going to prompt for input. We're going to mash our keyboard, and it's going to read that input, right? It then does some math. KMS is equal to KMS per mile times miles, right? That would be multiplication, right? It's just going to compute the number of kilometers. And then it's going to print out that whatever miles is equal to whatever kilometers, right? So we're going to understand each and every one of these lines and all the nuance and details as we go along. But I want to go ahead and run this program just to demonstrate it. Right? Let's go to, we're in the wrong directory here, so let's go lecture. This is going to be the wrong section, but that's okay. I'll go ahead and, I'm copying it to the notes eventually anyway. In fact, let's go ahead and do that right now. Like I said, you're not going to have a slide deck or anything for this course. Instead, all the notes will be posted on GitHub, and you'll have access to them. That should come on. There we go. Now it's code highlighted, right? When you look on, when you look at the notes eventually on GitHub, once it's not live, right? I'm going to have to commit those and upload those to GitHub later on. But you'll have this to go on, as well as other notes as we go along here. Okay. But otherwise, let's go ahead and compile it. GCC KMS to miles, right? Note there that I didn't have to type a lot, right? In fact, I didn't type in very much at all. I just typed KM. That is the first two letters of the file that I want. And then I did this magic trick of auto-completion, which is tab, right? Now, there are several files with that name here, so I need to go ahead and complete it, right? And if you couldn't hear it, it was donking on my computer, indicating that there was not an exact match. You need to tell me which one you want. So .c, right? No news is good news. That means it compiled. That means it compiled into this a.out program right here. We can go ahead and run it and see what it does. a.out, right? And just like we thought, it prompts me for miles. I can go ahead and mash my keyboard here, say 120.5 miles. And if we convert that over to kilometers, it says 120.5 miles is equal to 193.9 and change kilometers, right? Very, very basic program, but it is still a little bit more complex than the Hello World program you did yesterday. We're going to use this to start identifying the major components of a program, but before we do, let's go ahead and discuss how that compiling process actually works behind the scene. This file is nothing more than a plain text file. It's not an Excel file. It's not a word processor file like you'd have with Microsoft Word. It is a plain text file. Okay. All source files are going to be plain text files, and they contain computer code in a particular language. A source file is then compiled, at least in C. Some other languages do this differently, but in C, a source file is then compiled into an executable program, which is binary. And we tried to open that up yesterday, a.out, and it wouldn't let us because it's just a bunch of bytes. There's actually a lot going on under the hood here, and I just want to demystify a little bit of it. We go from source file to assembly to machine code. All right, I want to show you that what it looks like under the hood just a little bit. Okay. All right, so I'm going to go ahead and GCC. Let's see, I need my commands here. Sorry. All right, let's go ahead and GCC -s KMS to miles. Now that's a little bit different way of compiling. What I'm doing here is I'm saying don't compile it all the way to a binary file and into an executable file. I want to see what the assembly code looks like. Okay, and that produces another file. Let me go ahead and give myself some more room over here. With KMS to miles.s. If I open that up, it's also a plain text file, but it's not very readable. This was kind of readable because we could kind of understand what it was trying to do by just guessing, right, line by line. But this, if I just gave you this without any context, would you know what it does? No, it's just a bunch of, it's not machine code, but it is intended for a machine, right? This is actually a language for the actual hardware, the actual metal in your computer. It does things like, say, mul SD, probably multiply something, right? MOV, which is move. Move that the contents of that register over into the contents of that register. Registers are how a memory is stored on a processor, right? If you were back in the 1960s, right, then you were programming like this. You were writing a direct assembly, and some people still do it to this day for optimization. Right? And if you ever take when you take a hardware course, you might be exposed to a little bit of basic assembly code where you actually program it in assembly. Right? Now let me go ahead and show you something else. -C here, KMS to miles. What that does is that says compile it, but don't link it yet. Right? That produces what's called an .o file or an object file. Again, if I were to open that up, it wouldn't let me, right? Because it's binary, right? It doesn't know how to display that stuff. We can use a utility to do it, like we did yesterday or on Monday. Hex dump, right? C and then KMS to miles.o. There we go. All right, and it's just a bunch of binary code, right? It's a bunch of numbers basically. Now, it has a bunch of letters too, right? If we're all humans, and the luckiest of us still have our 10 fingers and 10 toes, and so we count in base 10, 0 through 9. A computer doesn't have fingers or toes. They have zeros and ones, binary. 0 off, 1 on, 0 low voltage, 1 high voltage. That's how a machine works. Consequently, it's in base 2. There are other bases though, right? And this is hexadecimal. This is base 16. 0 through 9, that gives you 10 characters. A through F gives you 6 more. It's a way of expressing numbers in base 16. Some of it is readable, right? For example, please enter miles, right there. My original strings were preserved in the compiled program because, at the end of the day, it's still binary, but it's something we can actually read. The rest of this stuff is just machine language. Zeros and ones, binary. We don't know how to, we can't read this unless we're a machine. But a machine can read it. There's one more step, and I'm just going to go ahead and jump to the end here. Again, what we did before, KMS to miles.c. What it would do, it would produce that assembly code, then produce that object code, and then it would bring in external libraries. For example, stdlib, stdio, or the math library. We don't need the math library right now. Multiplication is built into the language, but other things are not built into the language like sine, cosine, square root. That's going to be in the math library. Anything complex that you'd find on your calculator, that's going to be in the math library. All right? But what it does as a final step is it brings that library and that library and that library and your code and links them all together to produce this a.out file. And just by simply using GCC, it does it all in one shot. But there's a lot more going on behind the scenes back there, right, that GCC is doing. It's also, and that's actually an oversimplification too. It's doing a bunch of code optimization, right? It's taking out your comments because those don't end up in your assembly code. It's doing what's called a preprocessor directives by bringing in these external libraries, all right? All right. I just wanted to show you that show you that it's actually way more complicated than it seems. It's not just one command. For us, it's one command, but behind the scenes, a lot of stuff is going on, right? Stuff that's not necessarily necessary for this course, but eventually you'll be exposed to at some point. All right, so program anatomy. What's the first thing you see here? This is a comment. It's a very special type of comment, right? Comments, what are they? They are human-readable messages embedded in code. For now, let me go ahead and get rid of the program. I'll copy it later, just so that we're not looking at it. We'll come back over here and look at it when we need to. All right, there we go. Give myself some more room. There we go. All right. So comments are human-readable messages embedded in code. Right? They are intended for humans, not for the machine. Right? That's why we need to be using regular old language. Now, there are there are different types of comments. One type of comment are single line comments, right? They begin with was that a forward slash or a backslash? Forward slash, 2 forward slashes there, right? And anything after that is ignored until the next line, right? So for example, let me come over here and let me go ahead and put a comment behind over here. This is a comment. But if I went to the next line with my comment, then that's no longer a comment, right? You can see that the comment is highlighted over here in green, but now this is highlighted in regular old font black, and that's not part of the comment, right? This would actually not compile right now because comment, is that an executable statement that C understands? No, right? So it's going to error out there. Let me go ahead and return it back up here so that it now is a single line comment. You don't have to put it after code. You can put it before code. Hello, right? There we go. That's also a comment, okay? You also have multi-line comments. Multi-line comments begin and end, or begin with a /*, and then they end with a */. So I could put multi-line comments down here, say like this, hello, this is a multi-line comment. Yay, right? And go down there. Anything between this /* and the */ is completely ignored. Doesn't matter how many lines you put in there. And then finally, this is a multi-line comment, but it has special formatting with it. There are 2 stars at the top, and then we've got this vertically aligned vertical line of stars denoting our documentation here. These are known as doc-style comments, right? Doc-style comments begin with a /*, and a vertical line of stars to offset them, and then of course they end with a //. Right? Get in the habit of doing this. Right? In fact, what you can do is you can just type // and then enter, and it starts doing it for you automatically. Right? Foo, bar, baz. Right? It'll automatically put in those vertical lines for you. Okay? Let me go ahead and restore what I had before, though. Get into the habit of writing those and writing good documentation. What we're going to be looking for your first couple of assignments are author, date, and the purpose of the program. Right? That's going to be worth the documentation points for the first few programs here. Right? We grade on documentation, style, design, and correctness in your hacks, but we just grade on completion for your labs. Okay? All right. Was there a question? No? Okay. All right. Again, all comments are ignored by the compiler, the system, et cetera, et cetera. The purpose of a comment is to communicate to other humans what the intent of the code was. Right? This is what it does. This is why I'm doing it. Not the how. Right? Comments should document, like I said, the what and the why, but not necessarily the how. Right? Let me show you bad comments. Right? This will eventually learn that these are variable declarations. Create the variables. We don't grade on spelling, by the way, either. We'll call it out, but no, because I'm not going to grade myself on spelling either. Create the variables I'm going to use, right? And then this is a comment. Let me go ahead and get rid of that one. And then what do we say that this probably does? This probably reads in input from the user. Read in input from the user. Right? Those are bad comments, right? Because the code is already self-documenting. Now you're just being introduced to C now, but eventually you will be, very C experts, and you'll be able to look at this line of code and immediately say, oh, there are 2 variables called miles and kilometers, and they're both of type double, right? You do not need this. These are like training wheels, right? That is called cruft, and we should not have that in there, right? I'll define cruft here in a second, but you should only have good, comments should only tell you the what and the why. This program is converting miles to kilometers because I needed a program to do that, right? Why are you doing this? Not the how, right? The how is the code, and the code is self-documenting, right? Like I said, for now, all of your programs should have an author header, and that's all we're looking for now, right? Comments should not be crufty, right? This is not all caps, but cruft, right? Unneeded clutter in your code. And if I documented every single line, that's cruft. Where do we get that term? I think it's either from Harvard or Yale. There was a building called Cruft Hall that was kind of old and nobody used it anymore. No classes were held in it. So what happened to all of the junk, right? You wanted to get rid of a broken overhead projector or a broken computer. What did you do? You took it over to Cruft Hall and you left it there, right? Eventually the building filled up with garbage, right? That's called cruft. Don't let your code be filled with garbage, okay? Your code should be self-documenting and the code itself should be telling you the how it's getting done. Okay? All right, what's next? What's on line 7, 8, and also 10? Right? We've got these special hashes. Hash include and hash define. Right? Those are called preprocessor directives. Right? And all preprocessor directives begin with a hash. By the way, a little bit of trivia that we did in this morning's class. Why is that symbol there called a hash? So where else have you heard that other than hashtag, hash, whatever? Like think food. Hash browns, right? What do you do to potatoes to cut them up? That's called hashing. You cut them this way, you cut them that way. The verb, that's a verb to hash, right? And so why do we call this the hashtag? Well, because it's vertical cuts and horizontal cuts. You're hashing up your potato there, right? You can include external libraries using the include preprocessor directive, right? And we've already done that for the standard library, which is the standard C, and then the standard input-output library because we're going to be doing input and output. We're going to be reading a variable in, and we're going to be printing messages and printing output down here. Right? And generally, they will end with a .h. It is stdlib.h and stdio.h. Those are called header files, which we'll talk about much later when we start writing our own header files. Basically, you don't want millions of lines of code in one file. So what you do is you start separating things out. This input-output stuff, we'll go ahead and put that into another file, stdio.h. This math stuff, we'll go ahead and put that into the math library, that math.h, right? All the other standard stuff, that'll go in that file, that'll go in that file, that'll go in that file, right? It is a way of separating stuff out so that you don't have a billion lines of code all in one file, right? Then you can bring them in and use only that which you want, right? I'm not bringing in the math library here because I don't need it. I'm only bringing in the standard library, which you always should do, and the standard input-output library because I'm doing input and output. If I wasn't doing any input-output, I wouldn't bring that in. Right? By the way, what will happen if I don't bring that in, but I am doing input and output, or output and input? What do you think is going to happen here? Warning and errors, right? Yeah, it's not even going to compile, and it will compile something, but it's going to be a bunch of warnings. You did not include the library that includes printf. I don't know what you're talking about. Printf? Are you sure that you didn't mean to include the standard input-output library? And yes, I did. I just accidentally deleted it, so I'm going to go ahead and restore it. Right? All right, so again, those two are standard. We've already seen them. But there's another one, example, math.h, right? Allows you access to functions such as sine, right? Which is the sine function. Well, if you've got sine, what else would you want? It's not the opposite, but cosine, right? Tangent, et cetera, all those trigonometric functions. And another one, sqrt. What do you think that that's short for? Square root, exactly. Now here's the history. Why did we abbreviate it to sqrt? Square root's too long. Put yourself in to type, yes, but put yourself in the 1960s, 70s mindset. You don't have megabytes of computers. You don't have gigabytes of computers. You don't have terabytes of computers. You have bytes or kilobytes of computers. If you can save on a few characters in your files by shortening it up to 4 characters instead of square root, right, however many that is, 5, 10 characters or something, you did it because you didn't have enough bytes to actually do that. To this day, almost every single programming language uses sqrt. Python, Java, C#, all of them abbreviate it to sqrt. Why? Because C originally did it. Actually, I think Fortran originally did it. But that's how it was done way back when, and we ain't going to change it. Right? That's why. Right? But that's a little bit of history there. You also have access to constants. m_pi, m_e. What do you think those are? First of all, hopefully this is pretty self-explanatory. What is it? Pi, 3.14159, right? They prepend this with an M and an underscore to say that it's the math library's pi. If you want to define your own pi, go ahead. If you want to define your own E, go ahead. But the math library defines them for you. Right? Don't define your own pi. Right? Use the math library's pi because it is as precise as it can get in a computer. Okay? 3.14, that's not precise at all, right? All right, we have this define here, right? Define KMS per mile to be 1.60935, right? Now, why would we want to define that? For the same reason we have constants over here, right? Define is actually called a macro, right? Let me go ahead and bring that out. There we go. Define it's essentially a cut and replace operation by the preprocessor, something that runs before compiling. So what happens here is the compiler the preprocessor, excuse me, goes through, and anytime it sees KMS per mile, what it's going to do is it's going to do a copy replace, right? And it's going to replace that value that you specify. In fact, that's how the math.py works, or m_pi. Let me show you what it looks like. By the way, you can do this trick if you hold down Command on Mac, probably Alt on a Windows machine, and you click something, it'll take you to where it is. Right? There's pi. It's defined as 3.14159 blah, 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 out to about 16 decimals of accuracy right there. And of course, this, by the way, remember, this is cruft. You don't need to tell me that it's pi when you already told me that it was pi over here. I would actually dock the C developers here for doing that, right? Anyway, they define a whole bunch of other things. For example, E, well, what is E? It's the exponent. It's actually Euler's constant, I think, right? 2.718, et cetera, et cetera, et cetera. M pi 2, that's just pi divided by 2. M pi 4, that's pi divided by 4, right? For radians and things like that, right? But from the most part, you're only going to use these standard ones, right? What are the rest of them? I have no idea. Somebody found them useful at some point. But that's how you can define a constant to be that thing. Anytime that you actually use pi, again, what's going to happen is it's going to come in, take this value, and replace that m_pi. Yeah, go ahead.
What's the difference between doing that versus just like making it an int or a float to say like this is?
Because you can always change it. Say I did double pi, maybe, right? Equals 3.1415, right? There we go. Now later on I change my mind. Pi is now 3, right? Or you know what? Now pi is 42, right? So it prevents me from doing something like that, right? This makes it a constant, and pi is constant. It should not change. These things are variables. They vary. They can change. This over here, once you've defined it, it don't change, right? Yeah? No, you can't, okay, you can edit this, but no, you cannot save it, all right? So it is read-only, and also it's already been compiled somewhere, so you'd have to recompile it anyway. Don't save it. Yeah, don't save it. You could definitely be underhanded and change stuff and then ship it, and but no, you can't do that on this IDE, right? But you can define your own stuff. And again, why you would want to do this is because it allows you to represent a single value in a single place. Now, I only used it once in this program. But suppose in another larger program, I was using kilometers per mile, like in 50 different places, right? By locating it in one place, if I need to make a change to make it more accurate, right, then I can. It's just one change instead of 50 different changes. Right? I don't know if that's accurate or not, but we'll go ahead and leave it. But also, it makes your code more readable. What if I had just not used a macro at all? What if I had just brought this number down and there's my code, right? Without any context, do you know what the number 1.60934 is? No. By giving it a macro, I'm giving it a human readable name, KMS per mile. Okay, I can guess that that's the number of kilometers in a mile, right? You can argue about whether or not it's a correct variable name. Maybe I should have written out kilometers in a mile. Maybe that's a better name. I don't know, but I'll go with what I did. Right? There are only two hard things in computer science, two difficult things in computer science. One is cache invalidation, and the second is naming things. So you can argue about what a good variable name is with your partner or with other people. You ain't getting anything done, though, by arguing about it. Just pick a sensible name and go with it. Right? Keep it simple. But macros allow you to have your code more readable, and what we call these are called magic numbers. Where did that number come from? I don't know. It's magic, right? 1.60, right? I just pulled it out of the air, right? We want to avoid magic numbers there. All right, what's the next thing that we see on line 12 here? That's our main entry point, right? For now, again, argc, argv, we'll talk about those later. Those are command line arguments. But we've then got an opening curly bracket and a closing curly bracket. Everything within there is going to be our main. That's the program that gets executed. Because every program needs a starting point. When you start a program, the program needs to know where it's starting, right? Generally, this is done in a main function or method. All right, I'll just leave it as a function there. Every single programming language will do this. Java has mains. Python has optional mains. C# has a main. If you have an executable program, it has to have a starting point. And all of them use the keyword or the name main, right? Because that's the main program. Then what you have is, what you have is linear control flow, right? A program will then execute top to bottom, left to right, just like we read in English, right? Line 14 will be executed. Only after that's done, line 16 will be executed. Only after that's done, line 17 will be executed. It goes top to bottom, left to right, right? That's linear control flow. Now we're going to look at other things that change that linear control flow, because sometimes you want things repeated. That's called a loop. Sometimes you want to do something or not do something or do something else based on some condition. That's called branching. Okay. What other stuff do you see? Forget about the lines of code for now. All right. Look at the little things. What do you see at the end of each line? A semicolon, right? It's kind of like writing. If you were to write an English paper, what would you put at the end of every sentence? A period. That way, somebody that's reading your essay knows, oh, that's the end of an idea, right? And then I go on to the next sentence. We have that in coding too, right? We have punctuation, right? Executable statements end with a semicolon, right? That's a semicolon right there. If you forget the semicolon, the compiler is going to let you know about that, right? So let's try to compile it again. By the way, another trick here, if you have a command that you don't want to retype again, you can always hit the up button, up, and scrolls through all of the commands that you did previously so that you don't have to retype it. Right, there we go. And it's going to say, wait, something happened. I expected one of these things, probably a semicolon there, right at the printf. The problem is actually on line 14, though, right? That's where I forgot my semicolon. All right? Questions? No? What other punctuation do you see? A what? This bracket right here? Yep. Good. Curly brackets. Opening and closing curly brackets denote what are called code blocks. They're similar to paragraphs. If you have sentence, and it's all part of one idea, you put it into a paragraph, right? And then you have another paragraph and another paragraph. You're basically chunking things together. Well, the paragraph of our main here begins right there on line, whatever it was, 12, and ends on line 24. What else do you see? What about that? It's not a curly bracket, it's a parenthesis, right? What are parentheses? Parentheses denote, are used with functions and function calls, right? It's from math, right? Just like math. Let me go into math mode here. And if I said f of x, right, from math, right, what is the function's name there? F. Why do we put parentheses there? To denote what the input to that function is. If I say f of x is equal to x squared, right? Then you know, well, okay, now I'll take that input, which happens to be 5. X is a variable. Sometimes it can be 5, sometimes it can be 7, sometimes it can be -3, right? And I will put it into this function, and I square it, and that's the result of the function. We have functions over here. Main is a function, and we have parentheses, and those two things are the inputs. F of x, y, if it's a 2-variable function, right? Here I'm calling a function, printf. And so I have opening parenthesis, closing parenthesis, and this is the input to the function. Right? Likewise, down here, two arguments to that one as well. So some parallels with English, some parallels with math. What else do you see as far as punctuation goes? Quotation marks, right? Double quotation marks, right? Double quotes, that is, quote, ... are used to define strings, which are sequences of characters. Right? Basically plain English. Plain English. But also numbers, punctuation, etc. Right? These are all what are part of the ASCII text table, ASCIItable.com. Right? Excellent resource here if you ever want to see what it's all about. For example, capital S, that's associated with the number 83. Right? And you can see here, capitals come before lower cases. And they come in order, A, B, C, D, E, F, G, alphabetic order. Right? There's some other things, I don't know why it's not showing everything, but whatever. Anyway, other things like, for example, the space. Every time you hit space, the space bar that is, that's associated with character 32. There's some that are hidden and not seen. I don't know why they're not doing it. Full ASCII table. Maybe ASCIItable.com sucks now. ASCII hyphen code. That's where I want to be. There we go. There's one for bell or alert. There's one for backspace. There's one for a line feed and a vertical tabulation and form feed. Where does all this terminology come from here? Right? Think back before computers. What did people type at? A typewriter. You type. You get to the end of the page. What happens? Ding, right? And then you push it back, right? Those are the bell there, the line feed, right? Manually rolling your drum on a typewriter. Those all are all modeled right here, right? Because the typewriters came first, and then this ASCII text table came later, and they were emulating actual typewriters there, right? But anything that you could type, for example, can you type an asterisk? Can you type a plus? Yes, those are part of the standard keyboard. The standard keyboard comes from standard typewriters, like old, like it's over 100 years old, right? Okay. Those are double quotes. What else do you see there? How about that guy right there? Comma. Commas are used to denote items in a list, right? Just like we do in English. I love cake, comma, ice cream, comma, and donuts, right? There's comma there, and the Oxford comma. And there is a coding Oxford comma that we'll talk about later, but don't worry about it for now. Something in the future that we'll use are square brackets as well. Those are used in the context of arrays. Don't worry about it for now. You can also use single quotes. Single quotes. For example, let me go ahead and go into code mode here. C are for single characters, not for strings, right? So for example, I didn't do it over here in this program, but I can create a character variable. I'll call it initial, and I'll set it to my first initial C, right? I would use a single quote here, right? And this will compile just fine, even though I'm not using it. But if I were to use double quotes here, the compiler would have a bad time with that. Probably just a warning, but that's not a single quote, a single character. This is a single character, and you gave me a sequence of characters. Yes, it is one character in the sequence, but that ain't the same thing. Right? So we've got single quotes to denote single characters. One last thing I'll draw your attention to is read between the lines. What don't you see, or what's not there? Spaces, right? There's vertical space right there, vertical space right there. I could have skipped that space right there, right? I could have skipped that space, and it would be syntactically correct, right? That space and that space. Does it look good? Is it readable? No. White space is used to make your code more readable, right? So make sure that you're putting in white space after some punctuation. Just make it look nice. Sometimes you'll put in blank lines. Now don't go overboard. Everything needs to be double spaced because you're writing that English paper and it's a minimum of 5 papers. So you double space it and actually you make it 1.75 spaces. so that, you've met your page limit there, right? Don't do that with code, right? Instead, what we want to do is chunking, kind of like writing paragraphs. This declares a bunch of variables. This prompts and reads input. These two lines, they belong together. I'm going to chunk them together by not putting a blank line between them. But this line does something completely different. So I'll put a blank line between them. This line does something completely different. Right? Alternatively, what I could have done is I could have declared these on two different lines, and I would not. There we go. And I would not put a space or a blank line between them because they're related to each other. Although this is a little bit better style here, just declaring them all in one line. Right? It's kind of shorter. Right? All right. All of this goes into style. Right? White space makes your code more readable. And in fact, one white space idea that I didn't talk about was indentation. Right? So once I'm in my main, I indent everything, and I indent it at the same level so that it's all nicely aligned. What if I didn't do that? What if I didn't indent that? I indented that by 2 spaces. I'll leave that 4 spaces. I indent that by a whole bunch of spaces. Is that readable code at all? Nope. Let's go ahead and fix it. What was that thing, or did I introduce that thing that helps you fix it? A style, KMS. There we go. And it reformats it for you. You do have to reopen it to reload it. Oh, it fixed everything for me. Nice. But get into the habit of writing it correctly to begin with. Right? Don't go all over the place. Indentation means that code at the same level and the same block should be indented and indented at the same level. Again, we do this in English. You've got your essay. Right now you need to write an outline for the essay. All right? Idea point 1, 2, 3. Oh, sub-idea 1A, B, C. You indent those 3 things, and it's all indented at the same level. But all the main points, 1, 2, and 3, they're all out here, right? You can have a sublist and a sublist and a sublist. Don't go too far, but that's the idea. And once again, vertical space should be used to chunk code, pieces of code that are related together. Can I tell you what a chunk is? No. Because you might look at a piece of code and say, these things are really related. And I'll go, those 2 things, that's really 2 things there, right? And we'd argue back and forth about it. What we're looking for instead, as when we grade, is consistency, right? With indentation, with variable naming, all that stuff. There are a whole bunch of different style guides. There's one style guide. In fact, if I asked the style of the CS50, it would say that I'm wrong, right? You should actually go to the next line here, that this opening curly bracket right here, that should go to that next line right there. That's because they're using an old style, KNR GNU style. I don't like that style. I like modern style. So what I'm going to do is I'm going to start it on the same line here. Now, the closing curly bracket, that's at the same indentation level of where you started, right here. Okay? There are other style guides. There's Google Style Guide. There's GNU. There's old school KNR style, right? Everybody can argue about that. All we're looking for is consistency. Okay? Any questions so far? No? Use and I'll put it in the notes here. You can use a style to reformat your code, but you should write it correctly to begin with. But if you ever get yourself into edit, and now everything is off, that's all right. Don't worry about tabbing over, making sure everything's correct. Go ahead and use a style and fix it. All right. Now let's get into the actual program itself. The first thing I see here are variables. Just like math, variables can vary. They can have different values. Variable values can change in a program, right? They could have the value 5 at one point in the program, and then you change it to 6, right? Then it changes somewhere else. It can vary. They can vary. That's why we call them variables, right? Constants are not. That's pi constant or the kilometers per mile. Those are constants. They're actually technically macros, but they're constants that don't change and that you don't want to change because nobody is redefining pi, all right? C is a statically typed language, all right? What that means for us, don't worry about the technical details there. It simply means that you have to declare a variable before you use it, okay? For example, let me come over here and let me move this down to here, right? Now, up here, I'm using miles on line 16, but I've only declared it on line 18. The compiler is going to complain about this. Miles, I have no idea what you're talking about because the compiler works top to bottom, left to right, just like our program. It's going to see miles. I don't see a variable declared like that yet. Oh, okay, it's on line 18. Well, that doesn't help me because it should have been before line 16, right? So it has to be declared before you can use it, right? 2, you have to specify the type and the name, right? Let me go ahead and tab that over. There we go. You have to. For us, we're going to start out with 3 variable types. Int is an integer, double is a floating point number, and a char is short for character, a single character. You also have to specify the name of the variable, the identifier. In this case, the type is a double. It's a floating point number, a fractional number. And then here are the names, miles and KMS. If you misspell it, KMS, right? The compiler will not understand what you're talking about. KMS, did you mean KMS lowercase? It is case sensitive. So make sure that you are spelling it correctly and being consistent about it. If you spell it incorrectly, then be consistent with your bad spelling, right? Otherwise, the compiler will complain about it. But spell it right. Spell it correctly, please. Right? All right, what are those 3 types of variables? First of all, we have an integer. It's a whole number, negative, positive, 0, okay? It's actually what's called a 32-bit signed 2's complement integer. Don't worry about that, right? Don't worry about the technical details. Know that you can represent the numbers 2.147 billion. Let me go ahead and put in some commas there to make that a little bit more readable. There we go. 2.147 billion positive, 2.147 billion negative, right? That corresponds to the numbers 2, negative 2, to the 31st, and 2 to the 31st minus 1. Now, do we have that limitation there? Well, first of all, integers. Real integers are infinite. It goes down to negative infinity, goes up to positive infinity. Does anybody here have infinite RAM on their computer? No, right? That would be extremely costly, but also impossible, right? Because you do not have infinite storage. So they have to store it in a finite amount of space. The finite amount of space that they've chosen is 32 bits. A bit is a 0 or a 1. So you have 32 of these zeros or ones, right? One of them is going to be used for the sign. Is it negative or is it positive? That leaves 31 bits remaining, right? With which we can represent the number 2 to the 31st minus 1. Why minus 1? Well, you don't start counting at 1, do you? You start counting at 0. And so that leaves only 483,647 on the positive side. It leaves 1 more on the negative side, though, right? And that's why that works the way it does. Now, how does that work? Think about it in decimal, right? If I said, I'll give you 4 digits, what is the maximum value that you can represent? 9999, right? That's 9,999. That is 10 raised to the power 4, the number of digits I gave you, 10,000, but you don't start counting at 1, you start counting at 0, so it's 10,000 minus 1. It's base 2 because that's how computers work, zeros or ones. If I were in base 10, though, same idea. You have 4 digits, you could represent 10 to the 4th minus 1 maximum, and then work the other way, and you can represent the same, almost the same magnitude in the negative direction. What happens if I took this number and I added 1 to it? We'll find out about that on Friday, right? And you'll find out about it in your lab next week, right? It's called overflow, right? If you have a glass of water and it's full and you try to put 1 more drop into it, what happens? It overflows and spills. And that's what happens in a computer, right? It's just that it does it a little bit differently. There's no water in a computer.